I'm going to be honest. This video is 20% information and 80% me getting excited. So we're just not going to start with the information. So if you want to tune me out and stop the video, you can. But there's some really cool applications to this section. In the introduction video, I said, wait, why am I not talking about signal processing and Fourier series and stuff like that? Because I'm going to talk about it here. Okay. So we're just going to start with an example, and then I'll tell you why this is exciting. But I realize that some people just want the information. So here you go. Integral of sine of 5x times cosine of 3x. Okay, so dx. The dx is important. Otherwise, this integral becomes much easier. Now, this is harder and more complicated than we think it should be. None of our other, we can't do a u substitution where u is sine of 5x, because sine of 5x, cosine of 5x, and cosine of 3x are all very different things. They have different periods. That's the only difference, just the period. But even still, it actually makes it impossible to use the methods that we've already talked about. So we're going to use something called, again, I've spoiled it. Oh, no spoilers. I've only spoiled it once, not twice. I've kind of spoiled it twice. We're using these formulas, product of sums. That if I have, well, there's a bunch of them. I have cosine of one angle and sine of another angle. So we're going to be using this one. Sine of one angle, cosine of the other angle. And that's just going to be 1/2 sine of their sum plus 1/2 sine of their difference. Okay, just the average. Ooh, the average, because 1/2 of two things added together is an average. Just going to be the average of the sine of their sum and the sine of their differences. So this is going to be 1/2 sine of their sum. What's the sum of these two angles? 8x. Plus the sum of their difference. What's the difference of these angles? 2x. It doesn't matter which one you have first. Yeah. Okay, so here we go. That's it. It's easy now. Super easy. Let's fill in the last part of our table. Go all the way back to your notes. Product of sum formula. All right, and this is going to be whenever you have a sine of one thing times sine or cosine of another. Again, this will be sine of, how do I want to write this actually? We use A's and B's. Sine of AX times cosine of BX. And again, this could also be a sine. This could also be a cosine. I just don't want to write down 4 different cases. All right, and an example would be the integral of sine of 2x times the sine of 3x. So I'm not going to actually use our official example, our book example for this one, because I want to make it very clear that, again, they don't have to be different. They could both be sine, and we still use this method. All right, and that's the last main method that we've done. And now this integral is pretty easy. What's the antiderivative of sine? It's negative cosine. And then we have to divide by 8 because of the chain rule, basically. We have the 1/2 from before, right? This 1/2 is distributed. Antiderivative of sine is still negative cosine. And again, we have to divide by 2. So we get negative 1/16 cosine of 8x minus 1/4 cosine of 2x. And that's it. That's the end of the problem. We could check our answer by taking the derivative, and then check that answer by graphing on Desmos. Ta-da! No problem. So here's why it's interesting. All right. Here's why it's interesting. Again, this sort of technique especially is used a lot in signal processing. And what was the other one I was going to say? signal processing, and quantum mechanics. That's the one I always forget about, because of something called Fourier series. Now, there are so many books that can be written about this. I've only dabbled with the uses of Fourier series, but the idea is that for periodic functions, we can approximate a periodic function in this form. Now, this looks intimidating, but look at what it really is. A number plus a bunch of cosines being added together times constants, plus a bunch of sines added together. They should have parentheses here. That's weird. So we can write periodic functions as a bunch of sines plus a bunch of cosines with some constants. And what that kind of looks like is, like, let's look at, a periodic function known as a square wave. That's just 0, or that's 1.0. Hold on, let me zoom out so you can see it. Right? It just oscillates between 1 and -1. Is something on or is it off? Is another way of thinking about this. You can also use 1s and 0s, I'm pretty sure. I'm not an expert on this. But again, that's not a continuous function, which means that it's very hard to work with. But we can approximate it most of the time by these trig functions. Look at this. Look at the red curve. The red curve is approximating it with one trig function. Again, this is an infinite sum of trig functions. If we only approximate it with one, it's the red. If we approximate it with two, it's, I don't know. But as we approximate it more, we get closer and closer. So the yellow is the next best. I think that's 2. Kind of hard to see the yellow. And then the green gets better. And then the blue gets even better. And you can see that for all of these. Much more noticeable with the sawtooth, right? The red is not a good approximation. That's only 1. The yellow gets better. And the blue is really quite good for most of it. And then near the discontinuities, that's where things get even worse. Again, triangle and semicircle get actually some really good approximations. You can't even see the blue almost because it's just so similar. Or if you want to look at a periodic cubic function, you can look at it this way. So k equals 7 means that there are 7 sums. Again, technically there's going to be an infinite, but we don't deal a lot with infinite in applications when we're approximating. So we can approximate with 7 sines and cosines or 15 sines and cosines and get very close. Again, discontinuities really throw this thing up, because if you're approximating something that's discontinuous with something that's continuous, you're never going to get exactly there. So lots of cool stuff that you can use this for. And this is a really nice form to approximate these functions with, because discontinuous is bad. Especially if it's a messy discontinuous function or a messy function in general. But a function that's just sines and cosines, there's no squareds or cubed, just a function with sines and cosines, it's actually really, really nice, really easy to work with in terms of math. Sines and cosines, oh, really good. So that's kind of why this sort of stuff matters. Again, got the different coefficients here. And then, if we're actually integrating, this is where these coefficients come from. They come from integrals that we can either do exactly. Differential equations, partial differential equations, especially use this sort of stuff. Oh, lots of cool applications. But anyway, we're done. Bye-bye.